Okay, so let's go ahead and get started. So today, you're going to start building the Otter hardware. So the first part of it that you'll build is the program counter. And before we talk specifically about the program counter, there's some things from CP133 that you need for this assignment that we'll review. Okay. One other thing I just want to mention as being in class is you've probably noticed that I'm recording the lecture, and I think it was over the weekend. The first two meetings I put on Canvas. But the thing I wanted to talk about is that I can't guarantee the quality of these videos. Now, people that were in my CP133 class know about this, that last quarter, I think all but one, well, most of the lectures came out okay. Some of them, the resolution, not the greatest. And I found out over the break by talking to ITS that even though when you look at my computer screen right now, it's pretty clear, the video. Sometimes resolution is lost when there's the internet connection when you record to the cloud. So if the connection's not that great, it affects the resolution. So that's something out of my control. So that's why I can't guarantee that the quality is going to be the best. But I'll put it up there so at least it's something. Also, I don't know why this happened. Last quarter, one of the lectures, the audio was all garbled, even though I had the settings all the same, and I always test out the audio before I start the class. And actually, that happened again for meeting 2, my morning section. Again, my voice is all garbled. I don't know why. The other sections it came out fine. So anyway, I just wanted to put that out there because even though I'm recording, like I said, I can't guarantee, like if you miss a class, I can't guarantee that the recording is going to be as good as what the in-person is. Okay, because there's things out of my control. Okay, so I just wanted to put that out there. But I plan to have recordings of all the lectures. I usually put them on Canvas like a day or so after the class. Okay. All right. So the first thing we're going to talk about today is something from your CP133 class, because I'm sure you all talked about a MUX. MUX is short for multiplexer. And here's the symbol for a MUX. And MUXes always have 2 or more inputs, and they have just one output. Or this is So can anyone tell me how a MUX works? Does anybody remember from 133? Like we've got here 4 inputs, we have this one output, then we have this other input called labeled SEL, which stands for select. How does a MUX work?
So the select bits decide which input is going to be output.
Yeah, exactly. Yeah, the MUX, it acts like a multi-position switch. That whatever we have on the select input, that's going to choose which output gets connected to, or which input gets connected to the output. So since we have 4 inputs here, how many bits does the select input have to be? Right, 2, because of this, right? Remember, we talked about in the digital world, if you want to know how many values you can represent with a certain number of bits, it's 2 to the number of bits. Okay, so we would show that the select line is 2 bits by putting a 2 next to a slash, right? Remember that notation in 133 when you have a multi-bit input or output, you put a slash with the number of bits. Okay, and the inputs and outputs could be just single bit, or they could be multiple. Like each one of these inputs could be 32 bits, let's say. And the output has the same number of bits as the inputs. All right, so let's just make a little table, just again, to drive home how this mux works. So if my select is a zero, right, bits are zero, well, then the output's gonna equal this input tree. Right, and if I have a binary one on my select, well, then the output is just gonna equal input one. This is a two, a two, this is a three. Right, so everybody remember how that works? Okay, so now let's show what the Verilog or system Verilog code would look like. So I think I mentioned, I'm familiar with system Verilog. That's what I learned. That's what I teach in CP 133. But I do realize other CP 133 instructors use Verilog. So if you learn Verilog, use Verilog. Okay, that's perfectly okay. So you're going to start off with the name of the module. Now, I've also mentioned this before, and I'm probably going to keep saying it every class or almost every class, and that's be descriptive with your names in this class. Okay, not only with the module names, but also with your inputs and outputs. Like, with your inputs and outputs, don't do what I did here. Don't just call it out. Be more descriptive. Like if it's the out of a certain module, use that module name. And same thing with the inputs. But anyway, you would have your module name here for the mux. And then, you got to declare your inputs and outputs. Now, what kind of logic circuit is a mux? Is it combinational or sequential? Right, combination. Remember you have the two categories of logic circuits, right? Combinational, sequential. And what's the big difference between the two? If I have a sequential circuit, there's what? There's a clock because there's memory. Yeah, exactly. So yeah, memory, sequential, clock. If you don't have a clock, it's combination. There's no memory. Okay. So in system Verilog, if you have a combinational logic circuit like a mux, you're going to use an always home. You're going to use an always home block. Begin. Okay, now, if you had 133 with me, I had you use an if statement for the mux, right? Because the mux that we had in 133, at least again in my class, it was just a 2-to-1 mux, right? I mean, this is a 4-to-1. You also have 8-to-1, 16-to-1. Well, because it was just a 2-to-1 in 133, the if statement's not very long, right? It's just a few lines. Here, you're going to have muxes that have more than just 2 inputs. Okay, so I would prefer, especially for this assignment here, to use a case statement for the mux. Okay, so using a case statement, right after this begin, we write case, and then for a case statement in parentheses, you have what the sensitivity variable is, right? That when that variable changes, that's when the case is evaluated. So what am I going to use? What am I going to use as my sensitivity variable here? What is? Yeah, the select, right? Because the select is what's determining what's going on, right? Because the select determines which output gets connected to, or excuse me, which input gets connected to the output. So you say my select, you go in the parentheses here. And then I would just list my options. So, it's got 4 options here. There are 2 bits, right? Because my select is 2 bits. So you put the 2 tick mark. Now, what you probably did in 133 is then you put a B for binary, and then you would put 2 bits here since it's a 2-bit binary. But just to be a little bit different and show you that you can have a little bit of variety in system Verilog and Verilog. What I chose to do here, for no other reason, just to show something different. Again, you can do the B with the 2 zeros, that's fine. I decided to show the option as a decimal. So you see, you still put 2 here because it's 2 bits. But if you want to show it as a decimal instead of a binary, you just put D and then the decimal value. First option, 0. Okay, then it's semicolon, and then you would just put your output. And you would just assign it, whatever we call that input. Let's say we called it input 0. Now, another important thing that comes up here is the difference between an equal sign in Verilog or System Verilog and an equal sign with an arrow. And you both seen these, right? One's called blocking, one's called non-blocking. I don't really know where the names come from. But what's important is that when you have the equal sign, like if we had these two, when we had this code in either Verilog or System Verilog, what this is going to model is just a wire where A, B, and C are just the same node and the same wire. But if you have the same code, but you use the non-blocking symbol instead of the blocking, it doesn't generate a wire. It separates A, B, and C with circuitry that is going to be a latch. Okay, so here, if you use this code, right, B equals A, then C equals B, well, at the end of this, A equals C. But if you use this code with the non-blocking symbols, it doesn't generate circuitry where A is equal to C. A will not equal C here because it puts circuitry in between the A, B, and C. Okay? So the reason I point this out is because in this class, it's very important that you don't create unintended latches. Okay? In CP133, because the circuitry there compared to the circuitry here, namely that Otter hardware that you see, isn't as complex. Well, in 133, you could make a mistake where you use a non-blocking instead of a blocking in a always cone like this, which would create an unintended latch in your design, and your 133 circuit may still work. Okay, and that's because the circuitry being, again, simpler than what we have here, well, that added circuitry might not be enough to get it not to work right. It might slow it down some, because you're adding stuff that shouldn't be there. But since it's relatively simple to begin with, it'll work fine. Well, in that Otter, if you have an unintended latch somewhere, it's not going to work because it's going to screw up the timing. At the very least, it's going to screw up the timing. Okay, so you have to be very conscious of using the right symbol. You use blocking when it's a combinational. You use non-blocking when it's sequential, and in System Verilog, we use always FF for sequential. Okay, so that's just something to be very aware of from the very start. So you would just continue on here with the different options: 2, tick mark, 1, and when the select is 1, our out going to equal input 1. Okay, and you would just continue, you do the other two options. And then what do you have to end a case statement with? Well, end case, but what option? Yeah, default. So yeah, you have to have a default here. And then you just assign out something. Okay, then you need an in case as stated. Then you need to end this begin. And then you would end the module. Okay. Now, one other thing. Okay, if we had this, instead of 4 inputs, I have 3 inputs. I would still need 2 bits, right? Because I need 2 bits for 1, 0, 2 in binary. In your Verilog or System Verilog code, even though we don't have a 3rd input here, you would have to put in an option for that 3rd input. Like, you couldn't leave it undefined because if you do, that could create a latch. So you would put D tick mark D3, even though there's nothing connected to 3, and then just give it some output, just like another default output. Okay. All right, so any questions up to this point? Yeah. Is this sounding familiar? Because this should be stuff that you've seen before, right? Good. All right, well, let's move on. And let's talk about a register. Right, you talked about registers in CP 133. By the way, I think I mentioned this before, but anytime you see this triangle near an input, that means the clock, even if the clock isn't present. Okay, so what does a register do? Like, what's the purpose of a register? What does it do?
It's store memory.
Exactly, it stores, right? Because a register is a collection of what? Flip-flops, exactly. So it stores data. Right, it's made out of D flip-flops. Right, a single flip-flop can store a single bit. So a register is you just put a collection of D flip-flops together, and now you can store multiple bits, and that's a register. Now, your typical register is going to have a load input. LD stands for load. What does RST stand for? Resets. And then you have your in, and then you have an out, as you see here. And again, in your designs, you're going to be more descriptive than what I'm being here, right? You're not just going to say in and out, but you're going to be more descriptive. All right, so let's say that this register, the reset and load are active high, and they're synchronous. And also, this register is rising edge trigger. Okay. So with this information, let's fill out what's missing here, which is the output. And look at the note here. The note tells us that initially the output of this register is equal to 0011. Okay, that's at t equal to 0. That's what the output is equal to. All right, so now let's say we make reset 0, we make load 0, we put this data on the input, and then we clock it. Now it's rising edge, so that means the 0 to 1 transition of the clock is what matters, right? That at that time, that's when this is going to be evaluated. So if our active high reset is 0 and our active high load is 0, at the time of that 0 to 1 transition, what is our output going to equal? If we're not resetting and we're not loading, what is the output of the register going to do? Stay the same, right? Because that would be when the register is storing data, right? It just retains what it had previously. It retains the same output. So yeah, at the time of the clock edge, 0 to 1, if your reset is low and your load is low, they're both active high, so that means they're not active. Your output is just going to stay what it was. Okay? All right, but now what if we activate reset, make it 1, we leave the load 0, and now at the time of that 0 to 1 transition of the clock, what is our output going to be? 0, why? Yeah, it resets, right? That's what reset means. When it's active, the output just goes to 0. Okay. All right, let's look at the next one. The next one, reset's not active, load is active, right? So the load is active. So at the time of the 0 to 1 transition of the clock, what is the output going to be?
1, 0, 1.
Right, because see, load is the same thing as a write. That when the load is active, we're going to write, we're going to put the data that's on the input to the register that's going to be appearing at the output. So when the load happens, this data now is at the output. So this is something that can confuse people, right? Because here in the hardware, a load is just like a write. But remember when we were talking about the instructions right? In the ISA, right, the instruction set architecture for the Otter, we had those different load instructions, like load word, load half word. And when you do a load with your instructions, that's like a read, right? That's like you're getting data. Okay, and the instructions are write as a store. Okay, so that's just something you got to keep in mind. I know it can be confusing, but that's just the way it is. Okay, so the last one here is now both reset and load are active. Right, they're both one. At the time of the zero transition of the clock, what is the output going to be now? You have reset and load both active. What's going to determine what the output is?
Set, take precedence.
As long as you do that in the code. Yeah, exactly. Exactly, yeah. As long as you make reset the priority. So when you model it in Verilog, and I'll show you an example coming up, as long as you make reset the first thing that's going to happen, right? Give it priority, then it's going to reset in this case. And that's what you want to do in all your modules for the Otter that have a reset. You want to make reset the highest priority. So yeah, as long as your reset's the priority, this is going to reset. See, this would be considered a fringe case. You know, I talked about how this quarter you have to come up with the test cases for your designs. And when you're thinking about what test cases to use, first, I would advise that you think about, well, how can I make sure this thing is working the way it should work, right? You're testing the functionality. And then the second part is, well, what test cases can I give to try to break this thing? See, this would be a test case where you're trying to break it, right? Because you wouldn't normally reset and load at the same time. Okay. But if you did, as long as you gave reset the priority in your code, well, it should reset, and that would be something you would test. Okay. All right, so that's a register. Now a counter is just a register whose output will increment in binary by a certain amount. Okay, so a counter is just a little bit of an extension of a register that we'll get. All right, but if you're going to model a register in System Verilog, you would have the name, I'm calling it PC, the program counter, and then you would declare your inputs and outputs like you always do. Now we have a clock input, so this type or this register is what type of logic circuit, since we have a clock? Sequential, right? Because memory. So in System Verilog, what do we use for sequential circuits? We don't use always common, we use always FF. So you start with an always FF. And then we also have to put the edge of the clock that we're using. All the modules in the Otter are rising edge. So you're always going to use rising edge. So in the code here, you put positive edge, same as rising edge. So that means this always FF block is going to be evaluated on every positive edge of the clock, every 0 to 1 transition of the clock. Okay, then you have a begin. Now, for the register, use an if statement. Okay, like I said earlier, for the much use case, but for our register, use an if statement. So we're going to have if, and since we're making reset the priority, that's the first one we're going to look at. So if reset is active, also in the Otter, your resets and your loads, and I think all your inputs are active high. We don't have any active low. Okay, so if it's high, we're going to assign the out. And here we use the non-blocking, right? Since it's a sequential circuit. So we've got a 4-bit output. So I could put 4 tick mark B and then 4 zeros, but instead what I'm going to do, just make it a little shorter. So you can do this in either System Verilog or Verilog, is I'm going to use hex. Right, since a single hex character represents 4 bits, since I only have a 4-bit output, I just need one hex character. So I can just put a single 0. But you still need the 4 tick mark there to indicate it's 4 bits. Okay. Then I have else if, load. If we're not resetting, we're loading. Well, then this is just going to be assigned to whatever I call the input. Okay, and then I'm just going to end. Yeah, remember in Verilog or System Verilog, when you have an if statement, you can have as many else ifs as you want, or you don't even need an else. But notice I didn't end this with the else. Right? I just had if, else if, and then I end. Okay, why did I do that? Why did I not put an else? Right, that's what creates the latch, right? So you see no else equals a latch. See, that's how we get the storage. Because if it's not resetting and it's not loading, since there's no else here, it's just going to maintain the output it had. Right? So that's how you get storage. That's creating a latch because we want a latch. Right? I mean, if you had some sort of if statement in a combinational circuit and you didn't put an else, that would create an unintended latch, right? Because you don't want a latch, you don't want memory in always home, right? A combination circuit. Okay. So any questions up to this point? All right, is this sounding familiar? Right, it shouldn't be totally new, right? It should be things that might have been a while ago, depending when you had CP133, but it shouldn't be the first time you've gone over it. Okay, well, finally to do stuff. See, this is now what you're going to be doing today. You're going to be building this program counter. And this program counter consists of a counter, which again is just a register with a slight extension, and a mux. Okay, you're basically going to take those two things you learned in CP133 and apply it to this new thing here in this class. Now, I talked about this last week. I think it was last week. Yeah, it was last week. I talked about the purpose of the program counter. Remember what the purpose is? Like, what is this program counter providing us at the output? See, this output connects to this input of memory.
It's the address of the instruction that we want to.
Exactly, that's exactly it. The purpose of the program counter is that it provides the address of the instruction to be executed. But remember last week we talked about the memory module. And the output of this program counter goes to this address 1 input of the memory module. And inside that memory module are our code segment, our data segment, our stack segment. And right now we're just interested in the code segment, which is contained within the program. And that code segment has our instructions, right? It has our program instructions, a machine code. And then remember that that memory, it's arranged in 32-bit words that are byte addressable, right? So each byte has an address, and there's 4 bytes in a row. So each row has an address that we call a word address. And each instruction is 32 bits, so each instruction is a word. So each instruction address is separated by 4. Your first instruction's at address 0. You guys should really be listening up here now. Are you taking notes or?
Yeah, I've got the.
Okay, yeah. Okay, thank you. So the instructions, the first one starts at 0, then the next one's at 4, then the next one's at 8, 12, and 16, and so on. Okay. So look at what we have within this program counter. We have this block here plus 4. And look, it's connected to the output where the address of the instruction to be executed is. And the other side of it goes to this mux here. It goes to one of the inputs of this mux. So you see why this is +4? Because after an instruction is executed, we want to increase the address by 4 for the next instruction. Okay, so that's why this is called a counter, is because as long as you're going through the program sequentially, you're going to increment the output of this program counter by 4 because that's where the next instruction is. Okay, now there's other inputs to this mux, right? The +4 is just this top input. We have these other inputs, and look at what these other inputs are. This input's connected to something JALR. And if you look on the diagram for the otter that's on your table, you'll see that that goes to another module. I think it goes to the address generator, or what is it called? The branch address generator. Likewise, you have another input to the mux, branch, and then JAL. You actually saw JAL last assignment, right? What kind of instruction is JAL? A jump instruction. Branches, we're going to talk about on Thursday. Next class, we'll talk about branches. Okay, branches are conditional jumps. You can say jumps are unconditional branches. Okay, and then you have these other two inputs that have to do with something called interrupts that we may or may not get to, depending how much time we have in the quarter. But the key thing is, these inputs to the mux here, what determines what gets connected over to the input of this program counter is this select line right here. And this select line goes to something called PC source. And if you look at your diagram, your otter diagram, can you see where PC source of this mux? Can you see where else it is on that diagram? Yeah, exactly. Up here. Okay, in the upper right-hand corner, you see CUFSM. What does FSM stand for? Ionic State Machine, right? Then right below it, you have CUDCDR. DCDR stands for decoder. All right, the CU stands for control unit. So these two modules together are the control unit. And if you look at the outputs, which are on the right side of the decoder, one of the outputs is PC source. Okay, look at the other outputs. ALU fund, ALU source A, ALU source B, and there's this RF, WR select. Can you tell me where those connect to, those other outputs? Are there other muxes? Yeah, exactly. How many muxes are in that diagram? About. Yeah, there's like a handful, right? And each mux select line goes to that control unit decoder. Okay, how about, okay, so we talked about this, and this is the CU decoder. Okay, how about this PC write? Where else is it on the diagram? The FSM. See, look, PC write is one of the outputs of the FSM, the control unit FSM. In fact, if you look at the other outputs of that control unit FSM, they're mostly their reads and writes. Okay, so your muxes, the select lines, go to the control unit, the decoder part of it, and your read and writes of your modules go to the FSM part of your controller. Okay. See, the reason why those two modules are called controllers is because those two modules control how the data processes or progresses through the circuitry. Okay? And the controller is one of the last, in fact, it's the last thing, provided we don't do interrupts, It's the last thing that you model, you know, it'll be like next month sometime after the midterm. Okay? Okay, but getting back to this. See, if we're going through the program sequentially, PC source is going to be a 0, which is going to select this input that is the address that we just, or the instruction at the address we just executed plus 4, right? Because that's going to be the next instruction to be executed. But if we're doing some sort of non-sequential progression through our program, like we're not going in order, we're jumping, well, then PC source will be one of these other inputs, because that's what will cause the program to jump, because it will change the address of the next instruction to be executed to something other than the next one. Okay, and we're going to talk in more detail about this later. Okay, right now, for this assignment, you just have to do a few things. You just need to model the mux, model the counter, you know, interconnect this all together. Okay, but I wanted to give you some sense of how this fits into the whole picture. Okay, so, you know, the answer to PC write is that it's coming from the FSM of the controller. Okay, and then, you know, memory, the output of memory where the instruction is going to be, well, that connects to your reg file. And you're going to build this next week. Next Tuesday, you'll build the reg file. So we're kind of working our way left to right in that diagram as we build this. Okay, so are there any questions up to this point? Because the next thing I talk about is to talk about the assignment itself, like how to go about and put this into Verilog, a system Verilog.
So output of the program counter is the address of the instruction.
Yes, right here, right at this PCL, that's the address of the instruction to be executed. And you see that goes to memory where the instruction is located. And, you know, when the read enable is active and you have a 0 to 1 transition of the clock because it's synchronous, so at that time, the memory module will now put the instruction here that it got the address for from the program counter. Then the instruction is going to happen, like it's going to get executed. That's what the reg file, the ALU, that's what that all does, that we'll get to later.
Okay. And why does it need to be a counter?
Well, the reason why it's called a counter is because of this +4, right? Because after an instruction is executed, as long as you're going through the program sequentially, well, the next instruction is going to be 4 from that address. So this output is going to increment by 4 as long as you're going sequentially. Now, if you're jumping or something, it could change. It's going to change by a different amount. It could change by like +18 or +20 or, you know, -20 or, you know, any divisible by 4 number.
Is there any like is there anything to like protect the computer if you try to jump to a part of the memory that isn't like per code? Like if you try to jump to
That's a great question. Not the Otter. Yeah, so it's possible. Yeah, that's a great question. It's possible that if you had a mistake in this program counter, you could even go out of the code segment, like into the data segment. Now, other microprocessors, they could probably put some, you know, fail safes in there. But I'm pretty sure the Otter doesn't have anything like that. So that's why you want to have good test cases and simulate things before it's all put together. Yeah. Yeah, I wonder if that's happened. I'll have to ask Dr. Hummel. He's taught this course a lot, you know, quite a bit. I wonder if that's happened with somebody. I'm sure it probably has at some point. Yeah, no, that's a great question. Yeah. Any other questions? Okay, so as far as what the assignment is, okay, so again, it's hardware 2. It's modeling this program counter. Now, again, I just want to remind you, the grading criteria is on Canvas, so make sure to take a look at that to see what you need to turn in. You know, it's going to get graded. You know, I know there's 3 major grading things. One is you've got to submit the elaborated design schematic, right? That Verilog generates from your code, and make sure it looks something like this. You also need to, you need to include the warnings. Now, one thing for the people that had me for 133, and I don't know if this applies to other people because I don't know what all the other instructors say, but one thing to do different in this class than what I told you in 133 is in the constraints file, and this isn't until towards the end of the quarter, because we don't put anything on the board until the end of the quarter. But while I think of it, I want to tell people that in the constraints file, at the very top where there's the 3 clock lines, what I tell people in my 133 is not to uncomment the third one, just uncomment the first 2. But in this class, you would uncomment all 3. Okay, and that's because, again, in 133, the timing's not that important. So if you get warnings about timing, it's no big deal. But in this class, if there's a timing issue, that's a big thing. And that's what that third line does. It actually has something to do, or it has to do with the frequency of the clock. So, you know, that's commented. It may not pick up on a timing error that you have. Okay, so that's why you want to make sure it's uncommented. But like I said, we don't need the constraints file till later on in the quarters. Yeah, so that's like one grading, like one big block of grading criteria. Then the other one is, let's see, there's test cases, and you got to show the simulation timing diagram. Again, you got to come up with the test cases. That's one of the things you're being evaluated on. And then the last thing is the code. Okay, the code to use. In there, make sure you're putting sufficient comments. Okay, I told the graders to look out for that. You should have sufficient enough comments where, you know, if you come back to it later, you know what you were doing. All right, but there's basically 2 approaches to modeling this in either Verilog or System Verilog. One is to do a structural model, and this is what I teach in my 133 classes. But again, not all instructors do the same thing. So a structural model is you would have a MUX file where the code is going to look a lot like this, and you would have a separate PC, okay, which is going to look a lot like this. And then you would have a top module that connects this all together. Now, do you remember about internal signals? Like, what's an internal signal? You need them when you're doing a structural model. Actually, you need them when you don't do a structural model too.
Is it the logic that you have to use?
Yeah.
That's the outputs.
Yeah, it's the logic thing where, well, in System Verilog, in Verilog it's something else. But when you have, when you're doing a structural model, anywhere you're connecting lower level modules to each other, like here we're connecting the output of this MUX to the input of this PC, right? They're both lower level modules. So I need an internal signal. Now I'm labeling it T1, but again, use something more descriptive. Don't use just T1, you know, like maybe use MUX out underscore PC in or something like that. Be descriptive, okay? You would also need an internal signal here, right? Because you got this MUX and also this +4 block, if you will. Now, if you're connecting a higher level output or a higher level input to something, you don't need the internal signal. So for example, you know, this connection here from PC out to the other side of this block, that doesn't need an internal signal, right? Because this output here is a high level output. Yeah, I mean, what I tell people is this, if it's been a while or you're fuzzy on this, I think most sections in 133 do a ripple carry adder. Remember where you had the adders as the lower level, and then you have to connect it into an RCA, a ripple carry adder, right? So some of those needed internal signals, like when you went from one adder to another, like a carry out to a carry in, you needed an internal signal there. But when you were going from a main input to a lower level input or a lower level output to a main output, you didn't need the internal signal. Okay, so this is going to need 2. Okay, so you'll have 2 where you got to define logic. Okay, now the way to take care of this +4, okay, in either your Verilog or System Verilog code, is just with an assign statement. We don't want you to, make an RCA. For this, I mean, you could make an RCA to add that for. That would be a tedious way. And we don't want you to do that. We want you to have the software do the work for you, the software to develop that out. So the way to handle that +4 is that in your top module, you're just going to use a single assign statement. Whatever you call this internal signal, you'll just assign it to this output, whatever you call it, +4. Okay, so it's just done with one assign statement. Okay. All right, so that's one approach, the structural model. I would think most people that have me for 133 would probably do that. You did a lot of it last, when you took it with me. But there's some instructors that they don't do a structural model. They just do a, I don't know what you call it, other than not a structural model, where they put all the code in one module. And you can do that, if that's what you learn, or if you want to try it, that's fine. It's just all this code is just going to be in one module. You'll still have, you can put inputs and outputs, your internal signals, you have the MUX code, you'll have the register code, and then you're going to need assignment statements again for those internal signals. Like you're going to still have to have something that, says that this is +4, whatever this is. Okay. All right. So let's see. Is that all I wanted to talk about? Do you have any questions about anything at this point? Let's see. Yeah, I think I didn't miss anything. Yeah, like I said, again, emphasize, you want to be very, cognizant of latches, right? Because latches will really screw this up.
For the adding for part, is the same, probably use the analog as.
It should be the same, because now again, I'm not as familiar with Verilog as you know. See, System Verilog is actually easy. Because like in Verilog, you have reg and wire. In System Verilog, both of those are just logic. And then what's the other thing? Because there's something in Verilog where you don't have an always home and always that, it's just always, right?
Yeah.
If it's just always, then you got to really make sure that you get the right sign. Okay. Yeah, here, when they see, the thing is, System Verilog is just like Verilog 2.0. It's just like an improved version. They made it more idiot-proof, if you will, right? You don't have to think as much, So actually, Verilog, if you know Verilog, you're kind of like a higher level, so to speak, right? You have to think more. Yeah, because like here, with the comb and with the FF, it kind of drives home that these are different. But yeah, you can use assign and you can do structural and Verilog, all that's the same. Did you use structural or just one module?
Oh, sorry.
Either, okay, good. Yeah, because when you get to this, it will have to be structural, right? You're not gonna put all this one, this whole thing in one module. So if you haven't done structural, you will eventually when we get to the very end, if not before. Okay, well, that should be it. You should have enough to do this assignment. And let's see, who's the ISA for this class? Blake. Blake will be here shortly, and I'm here if you have questions.